Chapter 25, Train Resistance Tractive Power. Introduction. Various force of the offer resistance the movement of the train on the track. The resistance may be result of the movement of the various parts of the locomotive as well as the friction between them and irregularities, track profile, atmospheric resistance. Train move at a great speed. Tractive power of the locomotive should be adequate enough to overcome the resistance and haul the train at specified speed. Resistance due to the friction of the resistance offered by the friction between the internal parts of the locomotive wagons as well as between the metal surface of the rail of the wheels of the train moving at a constant speed. The resistance of the independent of speed can be further broken down into the following parts. Internal friction, depending on the type of the bearing, lubricated tube, the temperature, the conditions of the bearing. In this case, the rolling bearings vary from 0.5 to 1 kilogram per ton. Internal resistance, the resistance consequential movement of the various parts of the locomotive wagons. Rolling resistance occurs due to the railway interaction account with the movement of the steel wheels and steel rail. The total friction resistance is given by the empirical formula, where the resistance R1 is the friction resistance independent of the speed, is equal to 0.16 ten-thousandths of the weight of the train in tons. Resistance due to wave action. The train movements with speed. There's certain resistance developed due to the wave action of the train. Similar track irregularities, longitudinal unevenness, difference with the cross level of the resistance moving the train, such as resistance different speed with no method of precise calculation. Their resistance formula, following formula, has been invoked based on the experience of the resistance due to the wave action in equals 10 hundred thousandths of the weight of the train and times the v of the speed of the train in kilometers miles an hour. Resistance due to wind. The vehicle moved with the speed with a certain resistance developed. The vehicle moves toward against the wind. Wind resistance consists of the side resistance, head resistance, tail resistance, and the butt exists. Exact magnitude depends on the size, shape of the vehicle, the engine speed, wind direction, while the velocity. Wind resistance depends on the exposed area of the vehicle, the velocity, the direction of the wind. Figure 25.1 V is the velocity of the wind. O is the angle. 0 is the angle. The horizontal component of the wind is the velocity of the wind times the cosine of the angle. Cosecant of the angle opposite movement of the train. When the normal exerts the maximum pressure with the actual active angle of 60 degrees, the direction of movement of the train. Shows the V sin and cosine angle 0. Direction of the wind velocity is V, and the angle 0, the direction of the train. When the resistance obtained with the following formula, R3 is equal to 0.000017 AV, or A is the exposed area of the vehicle is meters cubed. Meters squared. V is the velocity of the wind, kilometers an hour. The study also support the fact that the important fact of the effect of the wind resistance exposed to the area of the vehicle relatively velocity of the wind, vice versa of the vehicle. In fact, the resistance depends on the square root of the velocity of the wind. Following formula empirical is estimated the basis of the study. R3 is the wind resistance in tons over 0.0000006 WV2. V is the velocity of the train in kilometers, and W is the weight of the train in tons. 25.4 Resistance due to gradient. When the train moves with the rising gradient, it requires extra effort to order to move against the gravity, shown in figure 25.2. Shows the angle of the rail going up the wheel direction up the Q, D, C, 90 degree angle W, W and R angle A, triangle AOB slope the wheel rail 90 degrees. Assuming that the weight of the wheel is moving in the rising gradient OA, the following forces that act on the wheel: the weight of the wheel W with the act on more normal pressure, and with the rail with the perpendicular OA to resistance due to the rise of the gradient R4 with the axis parallel to the OA. The three forces meet the common point Q with the triangle QCD. Can be taken. The triangle forces also can be geometrically provided with the two triangles QCD and OA AOB similar to the form QCD. R is equal to W sin of angle 0, and triangle OAB equals R equals W times AB over OA. In actual practice, if the gradient very small, therefore OA is approximately equal to OB. Therefore, R is equal to W equals to AB over OB equals W times the percentage slope over 100. Or R4 is equal to W times the percentage slope over the 100. This mean of the weight is trained with a 50-ton slope with 1 and 50 of the reduced gradient of R4 is equal to W times the percent of the slope over 100 equal to 50 times 2 over 100 equal to 1 ton. It may be noted that here and there may be trains ascending with the slope of the extra effort required to overcome the resistance offered by the gradient in the position. However, to preserve the train descending with the slope of the resistance offered the gradient helps the movement of the train. 25.5. Resistance due to the curvature of the train negotiate the heavy horizontal curve extra effort required to overcome the resistance offered by the curvature of the track. The curve resistance caused basically because of the following reason. Figure 25.3. The vehicle cannot attempt itself with the curved track because of the rigid wheel at the base, while the frame takes the tangential position and what wheel tries to move in longitudinal direction along with the curve that is shown in figure 25.3. On the account, flange wheel, outer wheel, and leading axle will rub against the interface of the outer rail, given the rise in resistance of movement of the train. Alright, figure 25.3 shows the resistance due to the curvature. You have your cause of rubbing, tending of the derail, your play, your lead axle, causing of the rubbing, tending to derail, trailing axle. Your curve resistance can be sometimes resolved with longitudinal slip, which causes the forward motion of the wheel of the curved track. The outer wheel of the flange of the trailing axle remains clear and tends to derail. The position of the worsens further in the wheelbase along with the curve is sharp. The curve resistance caused by the transverse slip of the curve things create the friction between the wheel flanges and rails. Poor track maintenance and particularly bad alignment of worn out rails and proper levels also increase resistance. Inadequate super elevation increases the pressure of the outer rail, and similar to excess super elevation puts the greater pressure on inner rails and also contributes to increase the resistance. The value of the curve resistance can be determined by the following equation. Curve resistance is equal to C times Fg over R. F is the force of sliding friction, G is the gauge of the track, R means the radius of the curve, C is the constant, which depends on the various factors. Equation indicates that the curve resistance increase the gauge with the increase of the gauge width. The resistance inversely proportional to the radius increase with an increase of the degrees of the curve. Empirical formulas can be worked out with the curve resistance, which as the curve resistance of broad gauge R5 is 4/10,000ths of WD. Meter gauge is R5 3/10,000ths of WD. Curve resistance 2/10,000ths of WD, where W is the weight of the train and D is the degree of the curve. It means that 4-degree curve of the broad gauge of the curve resistance of the train weighs 250 tons would be 4/10,000ths of times 25, 250 times 4, or 0.4 tons. Compensated gradient of the curve. Curve resistance over the quiet. You can compensate off the side of the reduction gradient, in which for the effective of the curve resistance translate in terms of the resistance due to the gradient. The compensation of the 400 of percent or broad gauge 300% and 200% meter gauge and narrow gauge line. That every one degree of the curve there will be a clear throughout the solved examples below. Example 25.1, calculate the compensated grade of the broad gauge with a 4 per degree curve with the ruling gradient 1 in 20, 1 in 200. Gradient rule is 1 in 200 or 0.5%. Compensation of the curve is 0.400 times 4 is 0.1600%. Compensated grade is equal to 0.05% times 0.1600% or 0.3 equals 0.34% and 1 in 294. Special characteristics of the curve resistance. Certain characteristics of the curve resistance have been observed over the years. These are enumerated here. The curve increase with the speed of the train. The curve resistance upon the center angle of the curve. For example, there are two curves of different radii with the same center angle. The total curve resistance would be the same through the curve resistance depends on the weight of the train, the length of the train, no appreciable effect. The curve resistance is less new rails compared with on the old rails. Depending upon the various factors, the curve resistance can be low as 22/10 of a kilogram and per ton per degree of curve, which can track in good condition may go as 1 kilogram per ton per degree curve for the worn out rails and rough tracks, other unfavorable conditions of the track. Alright, 25.6. Resistance due to starting and acceleration. The track, the pace of the resistance station with the starting and acceleration decelerating. The various resistance files. Resistance starting of the R6 is equal to 5/1500ths of the W1 plus 5/10,000ths of W2. Resistance due to acceleration R7 is 28,000ths of A and W, whereas W1 is the weight of the locomotive in tons, W2 is the weight of the vehicles in tons, W is the total weight of the locomotive and vehicles in tons, W1 plus W2, and A is acceleration, which can be calculated by the finding of the increased velocity per unit time, V2 minus V1 divided by T time, where V2 is the final velocity, V1 is the initial velocity, and T is the time taken. 25.1 summarizes the various forces of resistance faced on the train. Part 25.7. Attractive effort of the locomotive. Traffic effort of the locomotive. The force the locomotive can generate with the hauling load. The traffic effort of the locomotive should be enough to haul with the train maximal permissible speed. The various attractive effort of the curve is available to different locomotive different speed, which enable the computation of the value of the tractive effort. The tractive effort is generally equal to the lighter greater of the hauling capacity of the locomotive. The traffic effort is much greater than the required line haul of the train when the wheels of the locomotive may slip. The rough assessment of the traffic effort of the different types of locomotives is provided in the following section. Alright, 25.7.1, steam locomotive. The traffic effort of the steam locomotive can be calculated equaling the total power generated by the steam engine work done by the driving wheels. Assume that P, the difference of the steam pressure between the two sides of the cylinder. A, the area of the position of the engine. D is the diameter of the piston of the engine. L is the length of the stroke of the engine. D is the diameter of the wheel of the locomotive. And T is the main tractive effort of the locomotive work done by the two-cylinder and steam engine. 2 times the difference in steam pressure, E times the area, times 2 times the length of the stroke, and work is done in the revolution driving the wheel of the locomotive. Traffic effort times circumference of the wheel on equations 25 to 25 13 pi of P times D squared times L times T equals T times D pi times D, or T equals PD squared over L times over D. In the clear, the attractive efforts increase with the increase the steam pressure difference of the diameter length of the piston, decrease with the increase the diameter driving the wheel of the locomotive. The diesel locomotive traffic effort of the diesel locomotive can be assumed with the following empirical formula. TE traffic effort over the time equals 308 times the RHP, which is rated horsepower of the engine, over the velocity of the kilometers an hour times the kilograms. 25.7.3 electric locomotive. The traffic effort of electric locomotive varies inversely with the power over the speed. The empirical formula calculating approximately with the traffic effort is followed for an DC electric locomotive. The traffic effort is equal to A over the velocity cubed. For an AC electric, TE is equal to A over the velocity to the power of 5, where A is the constant depending upon the various characteristics of the locomotive. The important characteristics of the three types of tractions are stabilized in table 25.2. Alright, 25.8. Hauling power locomotive. Hauling power locomotive depends on the weight exerted by the driving wheels. Friction between the driving wheel and the rail. The coefficient of friction depends on the speed of the locomotive. The condition for the rail of the surface. The higher speed of the locomotive, the lower the coefficient of friction, which is about 1/10 of the high speed and 2/10 for the lower speed. The condition of the rail with the surface wet, dry, and smooth. The roof of the rough and also plays an important role in the deficiency deciding the value of the coefficient function, and such for the very smooth, but the coefficient of friction will be very low. Hauling equals number of the pair of the driving wheels exerted on the driving wheel's coefficient of friction. Thus, the locomotive with 3-pair wheel driving the axle of 20 times the coefficient of friction of the 2/10 of the hauling power is equal to 3 times 20 times the 2/10 of a ton equals 12 tons. For example, 25.2. Calculate the maximum permissible load of the broad gauge for the 3 pair of the driving wheels bearing the axle load of 22 tons each with a pole straight level track of about 80 kilometers an hour. That calculate the reduction speed that the train has to run with the rising gradient of 1 in 200 would be further result in a reduction in speed, but the train has negotiated a 4-foot curve on the rising gradient. Assume the coefficient of friction to be 2/10. Hauling power locomotive equals the number of the pairing drive of the wheels times the WT exerted weight over the E exerted on each of the pair. Coefficient of friction 3 times 22 times 0.2 is equal to 13 2 tons. The total resistance negotiating the train straight level track on the 80 miles kilometers. The resistance due to the friction plus the resistance due to the wave action and traction irregularities plus the resistance due to the wind. Substituting the value of V with the 80 kilometers, assuming the total resistant hauling power and of 13.2 tons. Approximately 1,150 tons on the gradient of 1.200. There will be an additional resistance due to the gradient with equal to weight times the slope of the percent of the slope since of the hauling of the total resistance will be 1,114 1,114.8 tons. And solving the further equation of velocity of 48.13 kilometers an hour, reduction speed 32 kilometers an hour on the curve 4 degree rising curve gradient of 1 to 200. The curve resistance is equal to 16 10,000ths of weight. Hauling power locomotive the total resistance, therefore 13.2 times 16 thousandths for the weight over the 18 10,000 11 hundred thousandths for the weight Or too many zeros. Maximum suitability of the weight of the 1114.8 equation. So further, the velocity of 43.68 kilometers an hour. Further reduction equals 48.13 minus 43.68 is 4.4 kilometers an hour. Therefore, the maximum permissible train load is 1,115 tons. Reduction speed due to the residing gradient 31.87 tons. Further reduction speed during curvature 4.45 kilometers an hour. Our example 25.3. Compute the sequence grade of the train with the 20 wagons as the locomotive negotiating the given the following data. The weight of each of the wagon 20 ton with the weight of the locomotive 150 tracks after with the locomotive the 15 ton rolling resistance of the locomotive 3 kilogram ton rolling resistance of the wagon 2.5 kilogram speed of the train equal to 60 kilometers an hour. Rolling resistance due to the wagons, rolling resistance time of the wagon times the weight of the wagon's number of the wagons, rolling resistance due to the locomotive equal to the rolling resistance of the locomotive times the weight of the locomotive. See the total resistance equal to the rolling resistance due to the wagons, rolling resistance due to the locomotive. Total weight of the train equal to the weight of all the wagons and weight of the locomotive. Total train resistance equal to the rolling resistance depending on the speed, rolling resistance depending on the speed, resistance due to the wind, resistance due to the gradient. Where G is the gradient of the track and after the locomotive total resistance of the train. There's the steepest grade of the train will be able to negotiate 1 in 56. Alright, example 25.4. Calculate the permissible train load that can be hauled with the locomotive 4 driving the wheel with the axles. Load of 28.42 tons each with the broad gauge with a rolling gradient of 1 in 200. Maximum curve 3. Traveling speed of 48.3 kilometers an hour. Taking the coefficient friction about 2.2 tenths. The hauling capacity for the locomotive equal to the number of the pairing driving wheels times axle load coefficient fraction. Total resistance of the train is equal to resistance due to the friction, resistance due to speed, resistance due to wind, resistance due to gradient, resistance due to the curve. Hauling capacity total resistance is equal to therefore the maximum weight of the train is 1,740 tons. Alright, your summary. Where there are various types of resistant forces that oppose the movement of the train of the track, the resistance due to the atmosphere, track condition, gradient, curve of the other factor of the track after the locomotive should be sufficient to overcome the resistance so that the desired speed can be maintained. Steam locomotives have gradually been replaced by the diesel-electric locomotives. The Indian Railways numerous advantages of the electrical traction over steam and diesel traction. Chapter 26, Railway Stations and Yards.